Okay, in last class we have introduced a data structure called binary decision diagram, and with the help of this binary decision diagram we can represent any Boolean function or expression, and we have seen how to construct this particular binary decision diagram. So, construction can be done from your truth table, where we are going to get a binary decision tree, or we can use the Shannon expansion of your Boolean expression to construct the BDD, binary decision diagram. And after that we have seen some reduction rule. Basically, we have three reduction rule: one, elimination of duplicate terminals, removal of redundant nodes, and merging of duplicate non-terminals. With the help of these three reduction rule, we can reduce the BDD and we get reduced binary decision diagram. Okay. And in most of the cases, we have seen that we are going to get a compact representation of Boolean function if we use reduced BDD, reduced binary decision diagram. But when you look into the construction of our BDD, we will see that we are not putting any restriction on the ordering of variable the way it may appear in our BDD, and again we are not giving any restriction of the occurrence of variables in a particular part. It may appear in many places, because if you look into the definition, we are saying that a binary decision diagram is a finite DAG with an unique initial node. Okay. It is a finite DAG directed acyclic graph with an unique initial node, where all terminal nodes are labeled with 0 or 1. All non-terminal nodes are labeled with Boolean variables. So, if we are having a Boolean expression, we are having those particular variable in the Boolean expression, and the non-terminal nodes will be labeled by this particular Boolean variable, and each non-terminal nodes are having two outgoing edges, one represented by dashed line, which basically indicates it is the valuation of that particular variable is 0, and another one is given by solid line, which says that the valuation of this particular variable is 1. Okay. So, this is the definition of binary decision diagram, and we can construct binary decision diagram of any Boolean expression. And while we are talking about this, or when you look into the definition of this particular BDD, it is not talking about anything about your occurrence of the variables, how many times it should occur, or it is not giving any particular ordering. So, if you look into this particular binary decision definition of binary decision diagram, then we will say that this is a binary decision diagram. Okay. This is a simple DAG. We are having three variables, say it is a function of three variable f, x, y, z. So, x I am having over here, then this is dashed line indicated valuation of this x is 0 and valuation of this particular x is 1, like that y, z are another variable, and these are the two terminals known, one is 0 and second one is 1. So, if you look into it, you see that here in this particular case, this particular x is appearing twice in this particular part, because as per definition we do not have any restriction. Similarly, you can say that y is also appeared in two different positions, but they are in the two different parts. Now, in this particular case, if you look into it, then by looking into this particular variable BDD, we are going to see some problems. We are talking in that particular case, we are going to have the notion of consistent evaluation part and inconsistent evaluation part. So, when we draw this particular BDD, some of the part may be inconsistent. Okay, I will say why it is inconsistent. So, the valuation of this Boolean function will be done through consistent part only. Okay. Now, you just see that I am saying that this is x, variable x, here I am taking x equal to 0, and in this particular part I am taking x equal to 1. When value of x equal to 0, I am going to take decision of y, this is in this particular part y equal to 0, and in this particular part y equal to 1. After that, when I come to this particular node, then again I am going to take decision on x, then I am going to say that if I follow this particular part, then x equal to 0, and if I follow this particular part, then x equal to 1. Now, this is the way that we can see, and ultimately we are going to get this functional value. Now, if I follow this particular part in this evaluation part, it is simple that value of x equal to 0 and value of y equal to 0, and we are going to say that the functional value is 0 if x equal to 0 and y equal to 0, it is independent of z in this particular evaluation part. Now, if I look into this particular evaluation part, okay, I am showing by double line. Now, what happens? I am going to say that x equal to 0 and valuation of y equal to 0 and x equal to 1. Now, in this particular part, you just see that value of x is taken as equal to 0 and it is also taken as x equal to 1. Now, when we are going to look for the valuation of any particular function, at any instant, we can have only one valuation for one variable. Just say that if I am randomly writing one function, say f is equal to x y plus x bar z. Now, in this particular case, when I am going to look for the valuation or evaluation of this particular Boolean function, either I am going to say that evaluate it either x equal to 0 or I am going to say that either x equal to 1. So, for these two different combinations, I am going to get two different valuation. But in this particular part, what will happen? The value is treated as x equal to 0 as well as x is equal to 1, which is not possible and which is not permitted. So, in this case, we are going to say that this is an inconsistent part. So, that means we are having the notion of inconsistent part in BDD. If we look into the basic definition of BDD, that means the valuation of the function or evaluation of the function has to be done through consistent part only. That means we should not look for the inconsistent part. Now, due to this particular problem, we are trying to eliminate this particular problem, and in this particular case, what we are going to do? We are going to put some restriction on the occurrence of the variables, and in that particular case, we are going to put a particular ordering of the variables, and after putting this particular ordering of the variable, we are going to get ordered BDD, ordered binary decision diagram. So, in case of ordered binary decision diagram, that means variable will come in a particular order. Let us consider that x 1, x 2, x n be an ordered list of variables without duplication, and let B be a BDD, all of whose variable occurs somewhere in the list. Okay, now, we are considering an BDD where all the variables of this particular list is occurring somewhere in this particular BDD, and we are saying that this is an ordered list where duplication is not allowed. We say that B has an ordering x 1, x 2, x n if all variable level of B occur in that list, and for every occurrence of x I followed by x j along any path in B where I is less than z. That means, if we are going to follow this particular ordering, say x 1 to x n. So, when we draw this particular BDD, then x 1 must always come before x 2, or maybe x 1 always comes earlier point of x n. It should follow this particular ordering. So, when we are following or restricting this particular ordering of BDD, then you will find that one particular part only one, the variable will appear only once. That means, since it is appearing only once, so that multiplicity of valuation like x equal to 0 and x equal to 1, that we the way we have seen in the earlier example will not occur. So, that means, in case of ordered BDD, we are going to follow a particular ordering of the variable. Okay. Just a simple example, you see that I am having an BDD over here, and we are saying that we are having 5 variables x 1 to x 5, and we are considering this particular ordering. That means, x 1, x 2, x 3, x 4 and x 5, this is the ordering of variable. When we mention this particular ordering, then what we have to see that x 1 always must occur before x 2, x 3, x 4 and x 5. Similarly, x 3 must always occur before x 5 in any part in this particular BDD. So, if you look in any part, you will find that this is x 1, x 2, x 4, then we are having the evaluation value. So, now where it is saying that it is evaluating this particular ordering, that means, x 3 is not coming before x 2 in any of the parts. Similarly, x 5 is not coming before x 1 in any of the evaluation part. So, in this particular case, we are going to say this is an ordered binary decision diagram, and that means, the variables are following a particular ordering. Since they are following a particular ordering, duplication or occurrence of a multiple times of a variable in a particular part is not allowed. Okay. So, this is the way that we can say this is ordered binary decision diagram. Similarly, this is another binary decision diagram, ordered binary decision diagram, and in this particular case, we are following this particular ordering, say x 5, x 4, x 3, x 2, x 1. That means, when you look any evaluation part, in this particular part, the variable must occur in this particular ordering. That means, x 5 will come first, then x3, then x2, then it is coming to the terminal node 1. So, it will follow this particular. Now, when we are using this particular order binary decision diagram, then variable will appear in a particular order in any execution or any evaluation part of this particular BDD. So, appearing a particular variable multiple times in a particular part is avoided. That means, the notion of inconsistent part is avoided over here. That means, all evaluation parts are now consistent. So, this is the notion about ordered binary decision diagram. So, we are going to follow a particular ordering of the variable. Now, if you consider this particular BDD, such say I am drawing a random BDD over here. I think in last class also I have drawn this particular BDD. Now, slightly change the level over here. So, in this particular case I am saying that it is not an ordered BDD. Why it is not an ordered BDD? It is not following any particular order in any execution. Say if I follow this particular part, then the ordering is your A, B, C. This is the ordering of variable in this particular part. But if I follow this particular order part, evaluation part, then I am going to get the ordering as your A, C, B. Okay. You now say that A is appearing before B and C is all right, but in this particular part B is appearing before C, and in this particular part C is appearing before B. That means, it is not following any particular ordering of the variable. So, that is why it is not an ordered BDD. Secondly, we are saying that this is not a reduced BDD. Why? You can see some instances. Look into this particular node C. We are having a redundant test over there, whether C equal to 0 or C equal to 1, it is evaluating to 0. That means, this is a redundant test. So, this redundant test can be removed. Secondly, if you look into this particular two nodes, B equal to 0, it is evaluated to 0, here also B equal to 0, evaluated to 0. In this case, B equal to 1, evaluated to 1, B equal to 1, evaluated to 1. That means, these are you consider duplicate non-terminals. So, these two non-terminals can be merged to one non-terminal. So, since we can apply the reduction rule to this particular BDD. So, that is why it is not an reduced BDD. So, this is not ordered because we are not having the similar order in order part, and it is not reduced even. Okay. So, this is a simple example that I am giving. Now, we are having some impact of the chosen variable. Now, you can say that I am going to say that we are going to put a variable ordering. So, some x, I am having some variable x1, x2, x3 like that, say xn. This may be one variable ordering. Secondly, I can say that xn, xn minus 1, xn minus 2 like that up to x1. This may be another variable ordering. So, with the help of this particular variable ordering, I can get an BDD. I will say that this is your BDD B1. And with the help of this variable ordering, I can again have the BDD representation of the given function, and I said that this is your B2. Okay. Now, we are getting these two BDDs, but these two BDDs are representing the same Boolean function. Now, after that we will use the reduction of these things. So, we are going to get reduced ordered binary decision diagram. Okay. Now, in this particular case, we have to see what will be the size of B1 and B2. It may happen that the size may vary in both the cases. One may be a bigger one and one may be a smaller one. So, that means the ordering of variable is going to matter a lot for the size of our BDD. Okay. I will explain these things with the help of one simple example. Just say that consider this particular Boolean function f. We are saying that x1 plus x2, x3 plus x4, x5 plus xc like that up to x twice n minus 1 plus x twice n. That means, we are having twice n variables. So, this is a function of twice n variable, and this is a simple function. Now, in this particular case, if we choose the variable ordering x1 to x2 up to xn, x twice n, so this is one particular variable ordering, then in that particular case what happens, we can draw the BDD for this particular function, and the ordered BDD will have twice n plus 2 nodes, we will see. So, we can construct the BDD for this particular Boolean function, and that particular Boolean function will have 2 to the power twice n plus 2 nodes, and we will see that no more reduction can be possible, and we can say this is the reduced order binary decision diagram. On the other hand, if we choose a variable ordering something like that x 1, x 3, x 5, then up to x twice n minus 1, then x 2, x 4, x 3 up to twice n. That means, all the odd subscription I am going to put first and then even subscription I am going to put later on. So, this is also possible variable ordering. So, if you use this particular variable ordering, then we will see that total number of nodes that we will be having is your 2 to the power n plus 1. So, if we are having n twice n variable, the total number of your these things that nodes that will appear in this BDD is your 2 to the power n plus 1, and the earlier case it is twice n plus 2. So, we can see that there is a considerable difference of our size of the BDD, and it basically depends on the variable ordering. Just see, this is the BDD I have drawn. This is basically the same function x 1, x 2, x 3, x 4, x 5, x 6, and the variable ordering that we are having is your x 1, x 2, x 3, x 4, x 5, x 6. So, in this particular case, I am getting this particular BDD, I am having 6 non-terminal nodes and 2 terminal nodes. Now, if I change the variable ordering, then we are going to get this particular representation, this BDD. So, here the variable ordering basically I am taking x 1, x 3, x 5, x 2, x 4, x 6. So, this is the variable ordering x 1, x 3, x 5, then x 4, x 6, here x 2 is appearing like that. So, in all the evaluation part you will find that it is following this particular variable ordering. Now, when I am having this particular variable ordering, then you see that I am getting a bigger BDD. Okay. So, this is the same function I am representing with one ordered BDDs, where ordering is from x 1, x 2 to x 6, and the same Boolean function I am representing with another order BDD, where the order is different, and we have seen that the size is more. So, the size basically size of the ordered BDD depends on the variable ordering. And if you look into this particular things, no more reduction rule is possible for this particular BDDs, and on the other hand for this BDDs also no more reduction rule is possible. So, these are basically reduced ordered binary decision diagram. Okay, so, that is why we are saying that a BDD is said to be reduced if none of the reduction rule can be applied. Okay. And similarly, for ordered BDD, ordered binary decision diagram, we are going to say that it is a reduced ordered binary decision diagram ROBDD if none of the reduction rules can be applied any further. Okay. So, eventually we are coming to reduced ordered binary decision diagram. So, it is a binary decision diagram. So, variable are having a particular ordering. So, we are going to say this is the ordered binary decision diagram, and thirdly it is a reduced one, no more reduction rule is possible. So, we are going to say this is reduced order binary decision diagram, and eventually we are going to work with ROBDD, which is having all the required properties for us. Now, in this particular case, you just see that already I have mentioned about this particular ordering of variables. Depending on the ordering of our variables, the size of our ordered BDD will vary. In some cases, we are going to get a compact representation, and in some cases, we are going to get slightly bigger representation or bigger ordered BDD or bigger reduced ordered BDD. Now, how to get the proper variable ordering so that we can get a compact representation of this particular Boolean function. So, that means we have to look for the proper variable ordering, but to get the proper variable ordering, to get a compact representation of the function in BDD is a hard problem. We do not have any method or we do not have any algorithm to say that this particular variable ordering is the best variable ordering, and it will give us the compact representation of a given Boolean function. So, this is a hard problem. It is difficult to find out that particular best variable ordering. So, this is a open problem, people are still working on it, whether it can be solved or not. Since it is an open problem, it is a hard problem. So, currently we are using some heuristics, and with the help of this heuristic method, we will try to find out some variable ordering which are going to give us some compact representation. It may not be the minimal one. The BDD that we are going to get may not be a minimal one, but it is going to give us some compact representation. So, we apply some heuristic, and by using this particular heuristic, we try to find out some variable ordering, and after that we apply this particular variable ordering to construct the BDD, and in most of the cases we have found that we are getting a reasonably good size of BDD representation of any function. Okay. Now, we have introduced a data structure called BDD, binary decision diagram, which is used to represent any Boolean function, and later on we have seen that ordering of the variable and reduction of that particular ordered binary decision diagram, and eventually we are coming to ordered binary decision diagram, and then we use this particular ROBDD to represent any Boolean function. Now, after that since we are having this particular BDD representation of Boolean function, we may need some algorithm or we need some method to work with those particular BDDs. Now, once you just see that I am giving a Boolean function and you have come up with a variable ordering, or you have chosen a particular variable ordering, then you are going to construct the BDD or ordered BDD for that particular function, and you can very well construct it with the help of Shannon expansion of the Boolean function. But eventually, whatever you are getting it, whether it will be reduced one or not, you have to check it, or if it is not a reduced one, then you have to construct the reduced BDD, reduced ordered binary decision diagram. And already we have mentioned that we are having 3 rules to go for the reduced BDD, and we can apply this particular 3 rules to the initial BDD. Now, we are going to see an algorithm. We are going to put this particular rule in an algorithm form, and we will say, or we will get an algorithm called the algorithm reduce, and we will apply this particular algorithm reduce to reduce any BDD. So, basically what will happen in this particular algorithm reduce, we are going to give a BDD, or basically we are going to give a ordered BDD as an input, and the output that we are going to get a reduced order BDD, and the variable ordering of the output BDDs will be same as with the input BDD. So, we will look into this particular algorithm. So, if we are going to look an ordering of some variables, say x 1 to x l, that means we are having L variables, then we can have at most L plus 1 layer in our BDD. So, we are going to have L plus 1 layer at most, but in some cases, in some part it may be less also, because that particular function may be independent of that particular variable. The algorithm traverse this particular, that algorithm reduce will traverse that B, that binary decision diagram B, layer by layer in a bottom up fashion. So, we are going to have a representation of our Boolean function BDD representation, and this algorithm reduce is going to traverse it from the bottom layer to the top layer. So, that means we will start from the terminal nodes, and after that we will traverse it back to the root nodes, and eventually we are going to apply some rules, so that we can get the reduced BDD. Okay. Now, here in this particular case, we are going to assign an integer label to each node. So, first one is the labeling of the nodes. Actually, say if I am having some BDD something like that, say this is your x, this is variable y, we are going to have some ordering. So, in this particular case, we are going to assign some integer label to each node. I can say that I am assigning that integer label 3 to it, and I am assigning that integer label 2 to it, and I am going to say that integer label 4 assigned to this particular thing. So, this is an integer label of this particular node, and we are going to say that this is basically the ID of this particular node, the ID of the node. So, basically we are going to give an ID, and ID is nothing but the integer label of each node, and we can say that ID of a particular node n will be equal to ID of m if the sub OBDDs with root nodes n and m denotes the same Boolean function. So, basically if sub BDD denotes the same Boolean function, then we are going to give them the same your this things what you call integer label. Just I will say that this is one node, say labeled with your x, and say this is y. So, with evaluation 0 they are going to same node, and with evaluation 1 they are coming to same node. So, this is z and z. Now, in this particular case what will happen, you just see that and after that we may have this particular BDD. Okay. Now, for this particular node, say this is n I am talking about, and say this is m. So, once we take the value of x equal to 0, it is going to look for this particular sub BDD. Similarly, for this particular node also, if y is equal to 0, then if they are having the same. So, in this particular case, it is also x equal to 0, they are going to have the same sub BDD. Similarly, for 1, both are having the same sub BDD. That means, both these particular nodes are evaluating the same sub formula for value x equal to 0 and x equal to 1. So, in that particular case, we are going to give the same label to this node n and m. So, we are going to give some label or ID, and this label will be same for this particular nodes. Okay. So, if they are going to have the same sub BDDs, then their label will be same. This is the rule to assign the label to each and every node. And another one we are going to define, which is basically two functions, one is your low and one is your high. So, for every non-terminal node, we define a function called LON. So, this is basically low to be the node pointing to via the dashed line from n, and similarly we can have high of n, this is basically high. So, if I am having any node say n over here, so I can have the dashed line and solid line. Okay. So, in this particular case, the label of this particular node is 3 and the label of this particular node is 4. So, in this particular low of n, it is going to return this particular label 3, because it is low to be the node pointed to via the dashed line. So, it is pointing this particular node. Similarly, high will return the value 4, because it is pointing to this particular node whose label is 4. So, basically low LO, low and high HI are two functions. It is going to give me the nodes pointed by dashed line and a node pointed by solid line respectively. So, we are defining these two functions, and with the help of these things we are going to construct this particular reduce algorithm. So, first task is to label each and every node. Now, next task is to label the node. So, how we are going to label the nodes? So, label the first label, say 0 to the first 0 node it encounters. So, first basically say we are going to follow from the terminal nodes and following in a bottom up approach. So, first we are going to get some node 0 node, we may have 1 0 node and more 0 node labeled by 0, then we are going to assign a label 0 to those particular 0 node. Okay. And similarly, we are having some nodes which are labeled terminal nodes which are labeled with 1, and we are going to assign label 1 to those particular nodes. So, if we are having more 0 nodes, we are going to give the same label to those particular 0 node, and always we are going to give it 0, label 0. And we may have more 1 nodes, to all the 1 nodes we are going to get label as 1. So, basically this is the starting of our labeling algorithm, and we are starting from the terminal nodes and we are going to follow the bottom up approach. Now, what we can say now, in this particular case we are giving that label 0 and 1. Now, later on what we are going to do, the nodes which are having the same label will be merged together. Basically, this is the second phase of our reduce algorithm. First, we are going to label each and every node, and next phase we are going to merge the nodes which are having the similar label. So, in this particular case, all 0 nodes will be merged to 1 node, and one node will be merged to 1 node labeled by 1. So, this is nothing but the reduction rule 1, that we have elimination of duplicate terminals. So, that means we are going to take care of this duplicate terminals 1. So, removal of duplicate terminals. So, all 0 node will be merged to 1 0 node, and all 1 nodes will be merged to 1 node. Okay. Now, secondly, if we are having now, once we label those particular terminal nodes, next we are going to follow in a bottom up approach, then we are going to get some non-terminal nodes. Labeling of non-terminal nodes, given an xi node n and already assign integer label to all nodes of layer is greater than I. That means, when we follow this particular labeling, So, this is I am coming level I, then I plus 1, then I plus 2, like that up to terminal level 0. When we come to label this particular node, then what will happen? All the nodes below this particular level must be marked. Okay, we should have all the integer labeling of all those particular nodes below this particular level. Then only we can label it. Since we are following the bottom up approach, so when we reach this particular node, then all the nodes below this particular node will be already labeled. If the label ID LON is same as ID HIN, then we set IDN to be that node of that level. That means, you can say that if I am having a particular node n over here and say low and high, both are coming to one particular node, say m. So, in that particular case, say ID of low n, say this is, say I can have say some level 3. So, ID of low of n is equal to 3. Similarly, ID of high of n is equal to 3. So, if both are same, then what will happen? We are going to give the same label to this particular node. So, I can say that this is also labeled with 3. So, what basically it means that now, in the next page we are going to merge them together. So, these will be merged together because they are having the same label, and you said that this is nothing but the reduction rule of redundant nodes, especially removal of redundant nodes, because here I am having some redundant test for both 0 and 1, it is going to give the same sub BDD. So, if the ID of low n and ID of high n is same, then n will get the label of this particular n only. Okay. So, this is basically we are labeling, putting an integer label, and basically it is going to help us to use this particular reduction rule, removal of redundant nodes. Okay. Next, we are going to say that already I have said that if I am coming to xi node, then all the nodes below that label is already marked. Now, if there is another node m such that m and n have the same variable xi, that means I am having a node n and I am having a node m, okay, and both are labeled with same variable, say xi. Now, what will happen in this particular case? If ID LON is equal to ID LOM, that means this is low and this is low. Okay. So, some label we are having, this is low, similarly high and high coming to the same nodes, or it may go to the different node, but both are having the same label. So, in this particular case, low n and low m is coming to the same sub BDD, and similarly high n and high m are coming to the same sub BDD, then ID of n will be equal to ID of m. So, if I am having already say ID of this particular node, say m say is equal to 5, then I am going to assign the same label to this particular node also, and it is 5. So, if you see these things later on, we are going to merge them together. Okay, that means we are, this is basically corresponds to the rule of removal of your duplicate nodes. Basically, these two are duplicates because they are having the same sub BDD. Below that, they are going to evaluate the same sub function. So, we can merge them together. So, this is basically nothing but the removal of this particular duplicate nodes. Okay. So, in this particular case, if it is not getting this two rules, say I am coming to a particular node xi and all the node below this particular node is labeled, and if it is not following these two particular rules, say this is the first one and this is the second one, it is not following these particular two cases, then what will happen? Otherwise, we set ID of n to be the next unused integer level. So, here starting with integer 0 for the 0 node, then we are starting with integer 1, then if they are not equal, then I will go to next unused number 2, then go to next unused number 3, like that. So, if it is not following these two particular rules that we have already mentioned, then set ID of n to be the next unused number. So, next unused number will be given to it, that means it is a new node we are getting, and it will be appeared or it will be present in our reduced BDD. So, once we are having these things, then what we are going to do, then already I have mentioned that the next phase what we are going to do, we are going to merge the nodes which are having similar label. Okay. That means, that can be removed. So, just we are going to look an example. So, this is an BDD, we are constructing x, y, z, and this is basically BDD also. So, if you look into it, how we are going to start it? First, we are going to start the terminal node. So, in this particular case, we are going to give 0 to all 0 node and assign one label 1 to all 1 nodes. So, this is the first rule labeling the terminal node. So, 0 and 1. Then we are going to look for this particular thing. So, in this particular case z, 0 is going to 0 node and 1 is going to 1 node. So, since these two are defined, so it is going to get a new label. Now, when we are coming to this node, say these two are having defined, so it should get a new label, but secondly already we are having a z node. So, we will compare these two nodes and the low of this particular z is same with low of this particular one and high of this particular z is high of this one. So, this node will get the same label over here, because they are having the same sum BDD for 0 and 1. And similarly, when I come to this particular node z label by z, again we will find that they are having two different nodes 0 and 1. So, it should get a different level, but if I consider about these nodes, then what will happen? The behavior is same. So, it is going to get this particular level too. So, now first we are labeling the terminal nodes, then we are coming one level up. Now, after label this particular node, then we will go to the next level. So, since I am having 3 variables, so total we are having 4 levels, 3 your these things what you call non-terminal nodes for 3 variables and one level is the terminal nodes. Now, similarly, now when we come to this particular node, you just see that low of your this particular node is pointing to that level 2 nodes and high of this particular node is level to this particular level 2 node. So, that means, in low of your this node is same with the high of this node. That means, this is removal of your redundant test. So, since they are same, this particular node is going to get this particular level. So, it will be labeled with 2. Now, when we come to this particular node, then you will find that low is coming to level 1 and high is coming to level 2. That means, low and high is not giving the same representation. They are having the different representation, different sub BDDs, different functions. So, it is bound to get a new level. Similarly, again behavior of these two nodes are not same. The third condition will also fail. So, it is going to get a new level and we are going to label it by 3. So, it is assigning a level 3. Now, when I am coming to these particular things, then low of this particular node is 2 and high of this particular node is your 3. So, ID of low is 2 and ID of high is 3. That means, they are having different sub functions. So, it is going to get a new level 4. So, we are starting from this particular terminal nodes and we are following the bottom up approach and coming to this particular root nodes and we have labeled all these particular nodes. Now, in this particular case, now next one is your merging of our duplicate nodes. So, if it is ID of low m n is equal to ID of low m and ID of high n is equal to ID of high m. So, this is the scenario, then we are going to merge it. So, merging of duplicate nodes, in this particular case these 3 nodes will be merged together. Okay. And secondly, we are having another one, removal of redundant nodes. So, if ID of low of p is same as ID of high of p. So, this is we are just saying that this is labeled with p and this is a level n and m. So, that is why I am saying that n and m. So, that can be merged and similarly, it can be merged. And now, since for this particular node p low and high are same, so we can remove these things. So, basically these are the rules that we are going to apply. So, in this particular case, now we can merge these particular nodes which are having the same level and eventually we are going to get this particular reduced BDD. So, this is the reduced order binary decision diagram of the BDD that we have starting on. Okay. So, now with the help of this reduced algorithm, we can reduce the BDDs and eventually we are going to get a reduced order binary decision diagram. That means, we are having an algorithm called reduce, where we are going to give an BDD B. Okay. So, that means, input is your ordered BDD, and what output we are going to get? The output of this algorithm is your ROBDD, reduced order binary decision diagram, and the variable ordering of the output BDD is same with the variable ordering of the input BDD. So, now you just see that we can construct a BDD for given any Boolean function, and after that, after construction we can use this particular reduce algorithm to get the reduced ordered binary decision diagram. Now, this is some properties we can see now reduced order binary diagram, binary decision diagram. So, the reduced ordered binary decision diagram representing a given function f is unique. So, if we are going to look at particular function f and we are going to construct the reduced order binary decision diagram of that particular function, then this particular binary reduced order binary decision diagram will be unique with respect to that particular variable ordering. Because if you change the variable ordering, then size will vary, because already we have seen. That means, we are going to get a different representation, different BDD. So, with a particular variable ordering, we are going to get an unique representation. Secondly, we are having a notion of computable variable ordering. So, if you consider two BDDs B1 and B2, if they are having the same variable ordering, then we say that they are having the computable variable ordering. Okay. And these two BDDs, B1 and B2, if they are having the computable variable ordering, and if they are representing the same Boolean function, then their structure is same. You just see that we are going to get a unique representation with a particular variable ordering. So, if two BDDs are having computable variable ordering, and secondly, if they are representing the same Boolean function, then these two BDDs will be identical. So, again, that is why you are saying that for a particular variable ordering, we are going to get an unique BDD ROBDD representation. Okay. So, that is why we are saying that ROBDD representation of any function is going to give us the canonical representation of that particular function. And secondly, already we have seen that how to apply this particular reduce algorithm, we are going to get a reduced BDD. On the other hand, you can apply this particular reduction rule also, and the order in which you are applying this particular reduction rule is immaterial. We are going to always going to get the same reduced order binary decision diagram. So, this is the unique property that we are having, that we are going to get an unique representation of a Boolean function with respect to a particular variable ordering. That is why we said that ROBDD gives us the canonical representation of Boolean function. Okay. So, this is the main feature of ROBDD, and we can use this particular BDD. Now, similarly, reduced order binary decision diagram, we are saying that if we are having two BDDs B1 and B2, and these B1 and B2 are representing say two Boolean function f1 and f2. Say we are having one Boolean function f1, and we are saying that this is the BDD representation B1, and we are having another Boolean function f2 and BDD representation B2. The ordering of B1 and B2 are said to be computable if there are no variable x and y such that x come before y in the ordering of by and y comes before x in the ordering of B2. So, we do not have such type of scenario, then we can say that this is a computable variable ordering. That means, in B1 if say x is coming before y, then in B2 also x must come before y. So, if y comes before x in B2, then we are not going to say that these two are having a computable variable ordering. So, now we can look for any variable ordering, and we can look for two BDDs. We will say that these two BDD we will have computable variable ordering if they are having the same variable ordering. Okay. Now, we can have any Boolean function, say if I am having a function x, y, z, say some random function I am going to say that x bar y plus x z plus y z. Now, if we are having such type of function, then I can always keep some choose some variable ordering, say I am going to choose a variable ordering x, y, z, and I can represent this particular function with the help of BDD b. And if we apply the reduction rule or we apply the reduced algorithm to this particular b, we are going to get a ROBDD. So, once we are getting this ROBDD, then what happens? It is basically nothing but we are representing this particular Boolean function. Okay, we are representing this particular Boolean function with the help of ROBDDs. Now, once we have this particular ROBDD representation of this Boolean function, now what can we do? Already we have mentioned that in most of the cases we are going to get the compact representation of our Boolean function, and after that we can do some operation, we can do some manipulation on those particular BDDs also. So, for any function we are going to have the BDD representation. Now, this BDD representation are going to help us to take some decision very quickly. So, what are those particular decisions? So, first one is I am talking about test for absence of redundant variables. Say if I am giving one particular function, can you say that whether this function is redundant of this is independent of some variable? Say if I am giving this particular function x y plus x z plus y z, can you see, tell me whether it is independent of some variables? This is a small function, we can see it and we can say that it may be independent, it may not be independent. But if we are having a BDD representation, then by looking into the structure of BDD, easily we can say that whether it is independent of some variable or not. So, how we can say that? If the value of a Boolean function, say f x 1 to x n does not depend on a particular variable, say x I, then any ROBDD which represent f does not contain any x I naught. Okay. So, if I am having a BDD representation of a function, say x is coming something like that, say this is y, so this is 0, 0 and say this is 1. So, this is a function f x, y, z. If I look into the BDD, in this particular BDD we have found that this particular BDD is not having this particular variable z. So, we can very well say that this function is independent of this particular variable z. So, test for absence of redundant variable is easily checked by looking into the structure of this particular ROBDD, because ROBDD is going to give us a unique representation with respect to a particular variable ordering. So, we are not going to get any other representation for that particular variable ordering. So, if one particular variable is not appearing in this particular structure, very well we can say that it is independent of this particular variable. Similarly, we can say that test for semantic equivalence, because with respect to a particular variable ordering, it is going to give me a unique BDD representation. Now, if I am giving you two functions, say f 1 and f 2, and I am asking whether f 1 is equivalent to f 2 or not, whether they are representing the same Boolean function or not, then what will happen? We are going to do some Boolean manipulation on this particular f 1 and we try to check whether we can get the f 2 or not. Now, if we construct now BDD b 1 for f 1 and BDD b 2 for f 2 with a particular variable ordering, that means they should have a computable variable ordering. Now, once we construct this particular BDDs for function f 1 and f 2, and eventually if we find that both are having the identical structure, then we can say that both f 1 and f 2 are representing the same Boolean function. That means, f 1 and f 2 are equivalent. So, the semantic equivalence can be checked very easily once we construct or once we have the BDD for these two functions. If they are having the identical BDD representation with respect to a computable variable ordering, then we can say that these two functions are equivalent. Similarly, we can say the test for validity. We know when we say that a particular variable Boolean function is valid or not. For all valuation of this particular variable, if evaluate to 1, then we can say that this is a valid function. So, in this particular case now, if we construct a BDD and if your BDD is your B 1, then we can always say that it is a valid function. So, basically we can say that BDD B 1, if it is a only terminal node, then we are going to say this is your BDD B 1. So, if I am giving any function f, now construct the ROBDD and with respect to a particular variable ordering, and if this ROBDDs happen to be your the BDD B1, then we can say that this is a valid function. So, you just see that if I am giving a long expression to check whether it is a valid or not, it is a difficult task. But if I am having a BDD representation and if BDD representation is B1, then we can very well say that this is a valid function. Similarly, test for implication, whether f implies g or not. So, f implies g. So, this is something like that, f implies g is equivalent to not of f or g. So, in this particular case, what I am going to do? I am going to have a take the negation of these things. So, negation of f implies g. So, if I take the negation, that means what happens? I am going to get the not of f or g, applying De Morgan's law. What I am going to get? This is your f and g. That means, if I am going to construct the BDD BF and not of, sorry, this is not of g, not of BG. And if this particular BDD is your B0, because I am taking the negation, you just see that. So, that means the negation is a contradiction. That means, if negation is a contradiction, that positive is a satisfiability. So, in that particular case, if this is equal to your B0, then we can say that f implies g. So, this is also, but how to do this operation we are going to check. We will discuss these things in our next class. Similarly, we can say that test for satisfiability. When we say that a function is satisfiable, if for at least one valuation or even one evaluation it gives the value as 1, then we can say that it is satisfiable. That means, if I am having a function say f x y z, then at least for one valuation this should give me the functional value as 1. Then in that particular case, we are going to say that this function is satisfiable. Now, how to check it? Now, we have to look for all valuation, or if we are having a truth table representation, we are having any one entry as 1, then we can say that it is satisfiable. So, if I am having a BDD representation of this particular function, and if this BDD representation is not equal to your B0, if it is not B0, then we can say that this is a satisfiable function. That means, if it is B0 for all valuation, it will go to B0, that means, for all valuation we are going to get 0. So, if the resultant BDD is not equal to B0, I can say that it is your satisfiable, because for some valuation it is going to get the terminal node 1. So, by looking into the structure, looking into the resultant ROBDD, because ROBDD is your a unique representation of the function and which is the canonical representation of the function. If the ROBDD is not equal to your B0, then you can say that the function is satisfiable. You just see that now, if we are having a Boolean function and if we can represent this Boolean function with the help of ROBDD with respect to a particular variable ordering, then some decision can be taken very quickly, like whether it is valid or not, whether it is satisfiable or not, whether this function is independent of some variables or not, whether two functions are equivalent or not. So, such type of decision can be taken very quickly. So, these are the advantage of using ROBDD. Okay, now, as a one question, I am saying that apply the algorithm reduce to reduce this particular BDD. So, I am giving an your OBDD, ordered binary decision diagram, and you apply the algorithm reduce to it. So, it is having 3 variable x1 and x2, x3, and the ordering is your x1, x2, x3. So, this is the ordering that we are having, and this is the given BDD. Now, apply the algorithm reduce to reduce this particular BDD. So, in this particular case, what will happen? First, I am going to label this particular nodes. So, in this particular case, what will happen? All 0 node will be labeled with 0 and all 1 node will be labeled with 1. Now, we are label this particular terminal nodes, then we go up. Now, in this particular case, when I come to this particular level x3, so it is 1 node is coming to 1 and 0 node is coming to 0. That means, your sub BDD is not same. So, we are going to have a ordering S2, and similarly, this is also in x3, 0 is going to 0 and 1 is going to 1. So, these are not same with 0 and 1, and secondly, these two are having the same level x2, same variable x3 and x3. So, sub BDD is so 0 for both the 0 it is going to 1 terminals, for both the 1 it is going to 0 terminals. So, it will also going to get the same level with this particular x3. So, both are labeled with your x2. Similarly, if I am coming to this particular node then if 0 is going to level 0 and 1 is going to level 2. That means, their sub BDDs are not same. So, it is going to get a defined level. So, I am going to label it with 3. When I come to this particular level with 0, we are going to this particular level 2, with 1 also we are coming to this particular level 2. So, in this particular case, it is going to get the same level with these two nodes. So, it is going to get x 2. Now, when I come to this particular node, 0 is coming to your 3 and 1 is coming to your level 2. So, these are different. So, in that particular case, it is going to get a new level and we are going to say that going to give a level 4. Now, this is now we are starting from the terminal nodes, going in a bottom up fashion and coming to the terminal nodes. This is root nodes and all leveling is over. So, in that particular case, now next phase is your merging. So, these 3 nodes are having the same level. So, we can merge together and ultimately, we are going to get this particular reduced BDD. So, merge all the nodes which have the same level. So, these 3 are having the same level, we are going to reduce it to 1 nodes and accordingly, we are redirecting this particular input and output. And so, ultimately, we are going to get this particular reduced BDD. So, another question you just said that consider this particular Boolean function x z plus x z dash plus x dash y. Is it independent of any variable? So, this is a function x y z and it is having involved this particular x y z. Now, we have to see whether it is independent of any variable or not. I think we can simply construct this particular BDD. So, this is your x if I am having the ordering. So, x equal to 0, I have to take decision on y. If x equal to 1, then I have to take decision on z. Okay. Now, if it is y is equal to 0, then it is 0 and if y is equal to 1, then I am having 1. Now, similarly, if it is x z, then if z is equal to 1, then what will happen? X equal to 1, z equal to 1. So, in this particular case, my functional value is 1 and if x equal to 0 1 and z equal to 0, then my functional value is your 0. Oh, sorry, x equal to 1 and z equal to 0. Sorry, this is not. So, in both the cases it will be 1 only, because x equal to 1, z equal to 1, it is going to give me 1, x equal to 1, z equal to 0, it is going to give me 1. So, in this particular case, I am having this particular redundant test. So, I can remove this one. So, in this particular case, eventually this is come to this particular point. So, this is the resultant BDD and in this particular resultant BDD, z is not appearing over here. So, we can say that this particular function is independent of z. So, this is a small function, we can do the Boolean manipulation also. What I am going to get from this function x z plus z bar plus x bar y, that means what I am going to get x z plus z bar is equal to 1. So, this is x plus x bar y, with simple Boolean manipulation also we can say that this function is independent of this particular variable z. But if I give a bigger expression, such type of manipulation may not be that simple. So, if you have that BDD representation, from this BDD representation we can say that this function is independent of variable z. Similarly, you just look into this particular function, very small function and simple function I am giving x z plus x z bar plus z dash. Is it independent of any variables? Is it test for validity? Can you look for the validity when I can say that it is valid if the resultant BDD is your zeros? Just try to construct it again. Again, I can say that I am going to take decision of your. So, this is a very simple. It is from this equation itself I can say that it is y is not there. So, it is independent of y. Okay. So, I am going to take x may take value as 0 and x may take value as 1. So, when I am going to construct it, when x bar equal to 0, then my functional value is 1. Okay. Now, when x equal to 1, then we have to take decision on this particular z. Now, when z is 1, then x z is going to give me 1 and when z is 0, x 1 z 0 is going to give me 0. So, in this particular case I am going to have this thing. Now, eventually what will happen, you just see that no, this is a redundant test. So, I can remove it. So, what I am going to get, this is your x, sorry, this is thumbnail. So, I am removing it. So, 1 edge will come over here. Now, just see that x is again this redundant test, x is equal to 0 is 1, x equal to 1. So, what happens from here, I can say that I am going to get this particular BDD 1. So, what are the BDD I am getting? This is the BDD B 1. That means, for all valuation the function is going to give me 1. So, since my resultant BDD is B 1, so what I can say that this is a valid function. Secondly, by looking into this particular function, I have said that this is independent of y. Now, after looking into this particular BDD, what I can say that it is independent of x, y and z. That means, this function is independent of all these particular 3 variables. So, let us see that by looking into this particular BDD, we can take the decision very easily. So, this is a small function I am giving, but if I am going to give a bigger expression, by inspecting this function, it will be difficult to say whether it is valid, whether it is independent of some variables, but once we get ROBDD, by looking into the structure of this particular ROBDD, we can take many more decisions quickly. Okay. With this, I will end up my lecture today. Thank you.